Today, we're going to talk about a single scientific paper. It came out in 1948, and it basically laid the entire foundation for our digital world. It was written by one man, a genius named Shannon, and it's called A Mathematical Theory of Communication. The thing is, he didn't just improve on old ideas, he literally invented a whole new field from scratch, information theory.
So to get started, Shannon had to answer a question that sounds, well, almost childishly simple, right? What is information? I mean, we use that word all the time, but what does it actually mean? From a technical, mathematical point of view. This one question is the key that unlocks his entire theory.
See, Shannon wasn't some philosopher sitting in an ivory tower. He was a hands-on engineer at Bell Labs. He was totally focused on solving a really practical problem, one that's been around since the very first smoke signals. Now, what's so amazing about this quote is just how simple and precise it is. And pay close attention to what it doesn't say. It says nothing about understanding the message or what it means or if it's true. For Shannon, the whole engineering problem was just about perfect reproduction. You send something from point A, and the exact same thing needs to show up at point B. That's it. To really dig into this problem, he created this brilliantly simple model that describes pretty much any communication system you can think of. You've got an information source, let's say that's a person talking. Then a transmitter, like a telephone, which turns that voice into an electrical signal. The channel is the wire that signal zips down. A receiver, the phone on the other end, turns it back into sound. And finally, the destination is the person who's listening. This simple model works for everything, from old-school telegraphs to TV to the internet today.
But every communication system has a villain, and Shannon gave it a name. Noise. Now, this isn't just the static you hear on the radio. It's any random thing that can mess up the signal as it travels through the channel. A crackle on a phone line, a smudge on a fax, a random flipped bit in a computer file. Yep, that's all noise. And it's the #1 reason a message might not get reproduced perfectly. So, to defeat this villain, Shannon knew he had to do something pretty radical. He had to completely separate the idea of information from the idea of meaning. It's a wild thought when you first hear it, but it was absolutely necessary to solve the problem. This slide just nails the key difference. Shannon basically declared that the semantic meaning of a message, what it's actually about, is, and I quote, irrelevant to the engineering problem. The crucial point is that a message is just one choice that was selected from a set of possible choices. So if I'm about to flip a coin and tell you the result, the information isn't the word heads. The information is the fact that we went from 2 possibilities down to just 1.
And this brings us to his powerful new definition. Information is the resolution of uncertainty. Before that coin flip, you're uncertain. After I tell you the result, that uncertainty is gone. It's resolved. So the more uncertainty a message resolves, the more information it contains. A message that tells you the winner of a 100-horse race contains way more information than a simple coin flip because it resolves so much more uncertainty. Okay, so if information is a real, measurable thing, what are the units? How do we actually put a number on it? Well, this is where Shannon borrowed a concept from physics and gave us a unit that literally runs our world today. He called the basic unit a binary digit, which his colleague John Tukey thankfully shortened to just bit. So 1 bit is the amount of information you get from answering a single yes or no question where both answers are equally likely. It's the information in one coin flip. And this incredibly simple binary choice, yes or no, on or off, a 1 or a 0, is the fundamental atom of all digital information. Everything you're seeing on the screen right now is just a massive, massive collection of these simple choices. Now, to measure the average amount of information coming from a source, Shannon used the concept of entropy. In his world, entropy is basically a measure of average uncertainty, or you could even call it surprise. Think about it. A source that just sends the letter A over and over and over again is completely predictable. There's 0 surprise, which means it has 0 entropy and it's sending 0 information. But a source that sends totally random letters, that's super high entropy, packed with a lot of information. This slide uses Shannon's own examples to show this in action. A string of totally random letters has really high entropy. But as you start adding the statistical rules of English, like the fact that the letter Q is almost always followed by a U, the text gets more structured, more predictable. The surprise factor goes down, and so does the entropy. In fact, Shannon calculated that the English language is about 50% redundant. That means about half of what we write is already determined by the rules, and the other half is our actual free choice. Okay, so now Shannon has his tools.
He's got a rock-solid definition of information, and he has a way to measure it, using bits and entropy. He is ready to go back to the battlefield and finally face his villain, noise. So what do you think? Back then, pretty much everyone just assumed that if a channel has noise, you will always have errors. I mean, sure, you can reduce them by, shouting louder or repeating yourself, but you can never get rid of them completely. It just seemed like a fundamental law of nature.
Shannon's first move was to define a brand new concept, channel capacity, which we label with a C. The best way to think of it is as the ultimate unbreakable speed limit for a given channel. It's the absolute maximum rate of information, in bits per second, that you can possibly push through that specific channel with its specific noise conditions. Every single channel, from a copper wire to a fiber optic cable to a deep space radio link, has a capacity.
And this right here brings us to the astonishing climax of his paper, the noisy channel coding theorem. Here's the punchline. Shannon proved that as long as your rate of transmission, your entropy, H, is less than the channel's capacity, C, then you can achieve error-free communication. Not just almost error-free, arbitrarily close to perfect. He showed that errors aren't inevitable at all. They're just the price you pay for trying to send information too fast. This idea completely flipped everything on its head.
And you have to understand, this theorem wasn't just some clever, abstract math trick. No way. It was a blueprint. It was mathematical proof that perfect digital communication was actually possible, and it laid out the core principles for how to get there. Shannon's paper became the mathematical foundation for so much of our modern world. I'm talking about everything from how we compress files into zips, to how a modem sends data over a phone line, all the way to how we talk to spacecraft millions of miles from Earth. It's all built on this fundamental understanding of information, noise, and capacity. His theory really is the invisible architecture of our digital age. So in the end, Shannon gave us the ultimate speed limit for communication. He proved what was possible. And for the last 75+ years, engineers have been in a race, a constant battle to see just how close they can get to that theoretical limit, always pushing the boundaries of how we connect and share information across the globe and even out into space. The game he started is still being played right now.